The other day, we were doing a crossword, and we talked about, or a matching, we talked about what a point was. A point does not have any size. If I underline something, you underline it. If I write something down, you write it down. You've got 90% of the notes in front of you, but we're going to add in the last 10%. It is represented by a dot, but the dot really isn't the point. The point is a location. And typically we name points in most textbooks with capital letters. So A, B, C. You don't have to put the word point in front. If you've got a capital letter, it's assumed that it's a vertex point, a vertice. All geometric figures consist of points. If you put together a whole bunch of points, you end up with a line. Typically, if I was going to name a line, I would use two letters, and I would use that symbol over the top. You could have more capital letters, more points, but two is enough. And typically we'll use two. Over here, you can see that we also have a lowercase letter. Sometimes we use lowercase letters to represent a line. Every textbook's a little bit different, every worksheet's a little bit different. You just got to be ready for whatever shows up. We've already talked about a plane being a flat surface. In drawings, in diagrams, a plane is usually represented by a parallelogram or some sort of four-sided figure. That does not mean that the plane ends right here. A plane is infinite, but can I draw something that's infinite? Not really. So I have to give it some boundaries just so I can draw it. This is just meant to give you an idea of where that surface starts. You have to think to yourself that it continues in all directions. If I'm naming a plane, I actually have to use the word plane. I don't want to use two letters like a line. If I said plane WX, that's not enough, because I could take a flat surface. Here's a flat surface, here's another plane. Couldn't I slide a plane right through W and X? Well, how do I know it's not this plane instead of the plane that's on the board? So I need at least three letters that are not collinear. W and X are collinear, WY are collinear, but all three are not collinear. I could put in another one if I wanted to, but I've got to have at least three. Sometimes, just like with my lowercase k up here, sometimes you'll see an italicized letter, something looks a little bit different than our normal point letters. So for this one, we could have plane, just put it a little bit diagonal, make it look a little italicized. Sometimes you can name it with one letter if it's a letter that's not connected to any point. We call point, line, and plane undefined terms. We have an idea of what they are. We know that a point is a location, but it doesn't really have any dimension to it. We know if we take a bunch of points that have no dimension, all of a sudden you get something that's infinite. And if you take a whole bunch of these points and spread them out over a surface, then you've got a plane. Those aren't really great technical definitions, but if we all agree or accept them, then we can build off of them. It's sort of like life. How do I know all of you are not figments of my imagination? I don't know. I just have to accept that you guys are here and that we're here. And then we go on with life. Same way with geometry. If you think that you know what a point, line, and plane are, then we can move on and do the rest of geometry. 2 points in a line, line segments, e.g., GH. Notice the difference between lines and segments. We don't have any arrows on our symbol. We have definite endpoints. Array has only one endpoint and then is infinite in the other direction. Doesn't matter what direction it is in the drawing. If it's ray AC, I'm pointing to the right. If it's ray DB, I'm pointing to the right. The symbol itself always points to the right. I think in section 1.1, opposite rays were mentioned. Do you have arrows here, here, and here on your paper? It shows up? Okay. Opposite to that. Well, I know that the definition is that we have to start with the same starting point. G, F. Opposite of E, about FG. Opposite of G, I'd be going back towards E. Opposite of F from G, so go towards H. As long as I'm starting at the same point and moving in the opposite direction. But you'll notice all of the symbols all point to the right in my symbolic way of showing it. What's the coordinate of L on that number line? Match?
-1.
-1. If you're on a number line, let's say you're living at L, it only takes one coordinate to find you. That's why we consider this to be one-dimensional. It only takes one dimension, one number, to find where you're at. If we're looking for a length that is on a number line, right here, right? Number line length. Let's see, Maria. Right? Maria is about 8 feet from the door. I'm about 20 feet from the door. We're in a straight line. How far am I from Maria? She's 8 feet away from the door. I'm 20 feet from the door. Well, what did you do in your head? Subtraction. Try to associate distance with subtraction. That's why, right here, you see that to find the distance between K and N, all we do is subtract the two numbers. Doesn't matter if they're negative or positive. -4 minus 2 gives me -6. That doesn't make sense because, at least in geometry, we want positive distances. When you get to trigonometry, you're going to have some negative distances, and that will designate something else. It'll have a meaning. Here, we're going to be dealing with positive distances. So, what's the very last thing that's happening with that -6? It's the last thing on this front page.
Absolute value.
Absolute value. So, we do a little subtraction, then we do a little bit absolute value. And this is for number line length. When we get to length on a graph, then we have a different formula. When we have length in a three-dimensional space, then we're going to have a different formula. When Etienne said that I was 12 feet away from Maria, he did subtraction in his head. Think about the slope formula. What is the slope formula from last year? What goes on the top? y2 minus y1, x2 minus x1. What operation is happening on the top and bottom? Subtraction. What did we just say you should associate subtraction with? Distance, length. That subtraction is finding a distance that we call rise. This subtraction is finding a distance that we call run. Start to associate subtraction with distance. Intersections. This takes some time to visualize. Some people get it right away, some people it takes a little bit of time. You have to think to yourself, or I do, I have to think of concrete objects, a surface, a plane, a line, a pencil. If two lines intersect, the intersection is a point. Draw from here right to here. So when I'm thinking intersection, I'm thinking touch. It's not a mathematical term, but it helps me remember what I'm supposed to know. Take a look at this first drawing. Do you see some tick marks or dashes right here? What does that mean? Raise your hand. Tell me what that means. Alan? Say that again. It went through underneath, behind. If you actually had a surface like this, and there we go. That's what you're looking at. This is Q. Remember, sometimes we can name lines with lowercase letters. So this is Q right here. It's going through, what are we calling this plane? M. M is sort of italicized. It's not really associated with a point. So we're going to call it plane M. And where is it touching? Like right here. What are we calling that point where it's touching the plane? That's point P. Then you've got a whole nother line here called, that's lying right on the plane like that. So that's what you're actually looking at. This is the three-dimensional representation. That's a two-dimensional representation of this. Then, for this one right here, what you're looking at are two planes running together. This one's running through this one. You're seeing something like that. These are finite. They end. But does a plane really end? No, it goes on forever. That's just to show you how they relate to each other location-wise. Where do they touch? They touch or intersect right there. Look at the front wall. Isn't the front wall of this classroom a plane? Isn't the floor a flat surface? Is it plane? Where does the floor of this room touch the front wall? There's a black strip up here. That black strip is like this right here. But you have to imagine to yourself that this continues forever. So if two planes intersect, you get a line, not just a segment. You got to imagine that it continues. Each of those surfaces continues forever, so the intersection continues forever. Down below, we've got a cube, and let's write that down. We're looking at a cube, so everything's at right angles in there. You have to imagine that those surfaces continue forever. Go ahead, try to fill out those four using that drawing. And make sure you're using proper symbols, proper letters, proper notation.